Dear students, in this video lecture, we are going to talk about the three different rules in phase diagram. The first one is the phase rule, the second is tie line rule, and the third one is lever rule. Let me begin with the phase rule. The phase rule is the generalization given by Willard Gibbs, named after the scientist Willard Gibbs, and he gave this rule. And it is also called as Gibbs phase rule, or simply it is called as phase rule. And the statement is, provided the equilibrium between any number of phases is not influenced by gravity, electrical or magnetic forces, or by surface action, and influenced only by temperature, pressure and concentration, then the number of degrees of freedom of the system is related to the number of components and phases by the phase rule equation F equal to C minus P plus N. In that sense, this phase rule gives the degrees of freedom, and this degrees of freedom depends on the component, and it depends on the phases, and it depends on N, where N is the variable. And if the variables are pressure and temperature, for our studies we are going to focus only on alloy system. As we know that in alloys there is no gaseous phase, we won't use this phase rule. We use the condensed phase rule. Okay, condensed phase rule, where we can see that the formula is C minus P plus 1, where N equal to 1. Since there is variation of temperature alone, there is no variation of pressure, we use condensed phase rule. And to understand better what is the degrees of freedom, we can see an example. And first we see this diagram. In this diagram, what are the phases present is, the first is we have the liquid phase here and solid phase here. In L plus alpha, liquid and solid coexist. So these two are single phase, and this is a two phase region. Now we see the example, we can calculate what is the degrees of freedom, and the formula is F equal to C minus P plus 1. Okay, since it is a condensed phase rule which is used for alloy system, it is C minus P plus 1. In all this example, we have it is an alloy system, means it is a binary phase diagram. Okay, where the component is two component. For example, if we take copper nickel, copper is one component, nickel is another component, so two components are there. So in all these examples, where the C value is 2, the C value is 2, and phase either it can be 1 or it can be 2. For example, in either it may be a liquid or solid, or liquid and solid coexist. We saw two single phase and one two phase region in the diagram. So to calculate the degrees of freedom, F equal to C minus P plus 1, substitute the values 2 minus 1 plus 1, which gives you 2. So the degrees of freedom for a single phase, one phase field is 2, and the degrees of freedom for a two phases is 1. So what do you mean by 1, 2? 1 means it is monovariant, and 2 means divariant, or it is bivariant. So what do you mean by that? In that sense, if the degrees of freedom is 2, then the composition and temperature can be varied independently. So in this region or in this region, composition can be varied independently, or temperature can be varied independently. There is no changes. It is still in the liquid region itself. And similarly here, the temperature can be varied independently, or the composition can be varied independently. Still it is in alpha phase alone. But in the case of a two phase region, either the temperature can be varied, in this axis, or the composition can be varied. Both cannot be varied together. Okay, that's why it said as it is monovariant. Okay, where the degrees of freedom is 1. That is the degrees of freedom. Okay, so either we can alter both composition and temperature, or we can alter any one that depends upon the degrees of freedom. And for example, a pure metal at solidification temperature is one component system, which means for example at this particular point, Okay, the pure metal is A at this point. Okay, so this point, and similarly if a pure metal, if it is B, then this point. And at this point it is only one component, means either B alone will be there in this situation, 100% B at this point, or 100% A at this point. Okay, so the component is one. If it is a one component, then phase is 2, because liquid and solid coexist at that point. It is 0. The degrees of freedom is 0, because we cannot get this, we cannot alter either the composition, or we cannot alter the temperature. If we alter the composition, then it is not, the component is not 1, the component becomes 2. If we change the temperature, then it will either only in liquid state, or it will be only in solid state. Only at this point, the liquid and solid, both phase is at equilibrium, so the phase is 2. Otherwise the phase can be written as 1 if the temperature is increased or the composition is changed. Okay, so that is the degrees of freedom is 0, and this particular point we say that as non-variant or invariant system. Non-variant or invariant system. So now you have a clear idea what is the degrees of freedom. Now we move on to the next rule, the tie line rule. So in tie line rule, it is a horizontal line drawn in a two-phase region. Horizontal line drawn in a two-phase region of a binary phase diagram to assist in determining the composition of two phases. Okay, it is also called as isothermal line, or simply called isotherm. If you see the example here, so this is the tie line rule. This is the tie line. Okay, it is drawn over here. So at constant temperature, we draw a line in a two-phase region, okay, where the two phases are liquid and alpha phase. This is a two-phase region. So here we draw this line to indicate what? To find out at what point it is completely in liquid, at what concentration it is completely in solid. At a constant temperature, at what composition it is in completely in a liquid state, at that particular temperature, at what composition it is in solid state, completely in solid state. That can be understood from the tie line. So the procedure is, a tie line is constructed across the two-phase region. The intersection at the phase boundaries on either side are noted. The perpendiculars are dropped to find the composition. So line is drawn here, and the intersection is, this is one intersection at this point, and this is the intersection at this point. Drop the perpendicular to find out what is the composition at which it is completely in liquid, and what is the composition at which it is completely in solid. And this changes if we change the temperature. Even you can draw a tie line here, even you can draw a tie line here, and the different temperatures, for different temperatures, the composition at which it is in completely in liquid, completely in solid will change. And the lever rule, it is an extension of the tie line rule. Okay, after drawing the tie line rule, if you want to determine, okay, if you want to determine, for example, if you consider a point here, B is the point. At this point, how much mole fraction it is in liquid state, how much mole fraction it is in solid state, that can be obtained. So by definition, we can define the lever rule is a procedure to find the mole fraction of liquid and solid phase of a given composition and temperature in a two-phase region, that is between the liquidus and solidus line. Okay, and liquidus and solidus line is this line is the liquidus line, the line which separate the liquid and the two-phase region. We call that as a liquidus line, and the line which separates the solid phase and the two-phase region, we call that as a solidus line. So when we, after drawing this line, if you want some certain composition, for example, let us consider C0 as a composition. At this point, if you want to determine how much mole fraction it is in liquid and solid, that can be computed using this formula. You can see this formula, S divided by R plus S, where S R, and in both the cases it is R plus S in the denominator. In numerator it is either S or it is R in the case of a solid phase. That can be observed from here. Okay, you can see here. So S means it is C alpha minus C naught will get you S, and R means C naught minus CL will get you R. And if you want R plus S, then C alpha minus CL will get you R plus S. you can see here it is C alpha minus C naught divided by C alpha minus CL. In both the cases it is C alpha minus CL in the denominator. The numerator alone will change, it depends on whether it is S or R. So the procedure is locate the composition and temperature in diagram. In a two-phase region, draw the tie line or isotherm line, and the fraction of phases is determined by taking the length of the tie line to the phase boundary for the other phase and dividing by the total length of tie line. So this is the how we calculate it, and using this we can calculate what is the mole fraction of solid phase and liquid phase. Thank you, students. We see you in next lecture.